Hello, welcome back to the Institute of Biostatistics. I don't think we need any introduction about the Institute, as we have been doing that earlier in a series of lectures. The last time we dealt with Bayesian analysis in three parts, and this time we are switching over to classifiers, another broad area. And the first part of the series is on Naïve Bayes classifier. So a classifier is a machine learning algorithm that is used to discriminate different objects based on certain features. One of the most common examples is an email classifier that scans emails to filter them by class label, spam or not spam. That's the case of machine learning, which is a subfield of artificial intelligence that allows computers to learn to perform tasks and improve performance over time without being explicitly programmed. For instance, take the case of a chess playing machine or computer. Each time it plays with a stronger opponent, it learns from the game and improves its performance. Some of the top classifier algorithms are Naïve Bayes, logistic regression, decision tree, random forest, neural network, support vector machines, k nearest neighbors, and k means clustering. We will try to cover some of these topics in the lectures to come. Naïve Bayes algorithm is a logic-based technique which is simple yet so powerful that it is often known to outperform complex algorithms for very large datasets. Naïve Bayes algorithm utilizes Bayes theorem, which we have seen already in the previous lectures. So it's about the conditional probability, which is P of B given A expressed by P of B into P of A given B divided by PA. Now we are trying to generalize this expression by replacing B with Y and A with a set of events, x1 to xn. So which can be expanded just like the simple Bayes theorem. And here x represents attributes of features and y is the response variable. Now, the reason that Naïve Bayes algorithm is called naive is not because it is simple. It is because the algorithm makes a strong assumption about the data having features independent of each other, while in reality, they may be dependent in some way. Anyway, this assumption makes the Bayes algorithm naive, which implies that given n different attribute values, x1 to xn, the joint probability or likelihood can be written as P of x1 to xn given y is equivalent to product of P of xi given y. In other words, it assumes that the presence of one feature in a class is completely unrelated to the presence of all other features. If this assumption of independence holds, Naïve Bayes performs extremely well and often better than other models. Now, this assumption also implies that the way x1 affects y is independent of the way any other xi affects y. Anyway, so under this assumption, P of y given x1 to xn can be written as this one, and there are no additional conditional terms. And as usual, as the denominator remains constant for a given input, we can remove that and express the equation as P of y given x1 to xn proportional to P of y and the product of these probabilities. Now we need to create a classifier model. For this, we find the probability of a given set of inputs for all possible values of the class variable y and pick up the output with a maximum probability. This can be expressed mathematically as argmax of this posterior probability. That based on the different values, we attain P of y given x, and we simply take the most probable or maximum of these values. So let us go to an actual illustration of this method. From a very commonplace example, suppose that we have a data set of weather conditions and corresponding target variable play. We need to predict whether the play would happen or not on a particular day according to the weather conditions. So to solve this problem, we need to follow the below steps. Convert the given data set into frequency tables. Generate likelihood table by finding the probabilities of given features. Use Bayes theorem to calculate the posterior probability. The problem here, once again, is that if the weather is sunny, would the game happen or not? So this is the data set we are having based on the past records on 14 days, 0 to 13. Now, depending upon the weather cast or outlook, the game happened or not, yes or no. So that is the data. From this data set, we make a two-way table, weather forecast, different conditions, and the game was played or not. And we also, there are 14 days altogether, and we can compute the marginal probabilities. What is the probability of a day having overcast, whether overcast, rainy or sunny, or whether the game was played on any particular day or not. What is the probability? We can also compute a probability, conditional probability of that a particular a day has a sunny forecast. What is the probability of the game happening? That is 3 out of 10. 5 plus 2 plus 3, 10. Now, with this data, we apply Bayes theorem. What is the probability of the game will be played on a sunny day? By substituting all this, and what is the probability of the game not being played on a sunny day? And here you go by the larger probability, that is, the probability of the game happening is larger than probability of game not happening. So we can say that the game on a sunny day, there is a higher probability of the game being played. So in case the question posed is whether we can play safely based on the weather forecast, we will need to consider Bayes risk. That means each of these probabilities will have to be multiplied by the associated loss, that is risk, and then go for to minimize the risk. Alternatively, we can associate one loss value or a loss value with each of these conditions, and we can multiply with the probability of the event and get a risk value, and then compute a maximum risk for the game not played and say played, and minimize that minimize that risk and select that particular action which has minimum of the maximum risk. That is called minimax rule. Anyway, the Naïve Bayes can also be used with continuous features, but is more suited to categorical variables. If all the input features are categorical, Naïve Bayes is recommended. It could be binomial or multinomial. However, in the case of numeric features, it makes another strong assumption, which is that the predictive variables are normally distributed. Sometimes a smoothing procedure is implemented in Naïve Bayes to avoid zero probabilities for certain levels of the response variable. This is called Laplace or Laplacian correction, achieved through adding a pseudo count of 1 or higher to both the numerator and denominator count while working out the conditional probabilities. Now we go for an actual illustration based on real data. The data comes from a case control study. For this exercise, the data were obtained from a study made with patients diagnosed with coronary artery disease, shortly called CAD, in a duration of less than or equal to 10 years, attending OPD of 2 hospitals. The patients having the disease were taken as a case group. It's a case control study, of course. And the control group included hospital controls without coronary artery disease in the ratio of 1:1, and there were totally 110 patients in each group. The objective of the study was mainly to find the association between two factors, that is, bowel suppression, and tear suppression with coronary artery disease. However, there were several other exposure factors, including dietary and socio-demographic variables. A sample of the data shown here for 10 subjects. There were 110 subjects under each group. CAD incidence, 1 or 0, CAD, and age of the patients, the DLP, family history, and so on, and bowel and tear suppression. The Naïve Bayes model was fitted using Naïve Bayes function of E1071 package of R3.6.2. The accuracy came to 0.8 and with a sensitivity of 0.81 and specificity of 0.78. These values are coming from the confusion matrix, that is a two-way table of predicted and actual values of CAD. Now, by changing the Laplace parameter from 1 to 5 or by doing a 10-fold cross validation, the accuracy level did not change. Now, the fitting was done repeated for several Laplace values. And 10-fold classification, 10-fold cross validation means every time from the data set, we remove 10 values of the cases or controls randomly. And then we fit a model and predict for that 10 deleted values. And this is repeated every time taking another set of random subjects. And the predicted values, these are pulled together and we compute the accuracy, sensitivity, and specificity. This was done, and based on the performance of different variables in their predictive ability or association, strength of association, we prepared this graph, and the most influential indicators were found to be tear suppression and palpitation. This is one of the actual case study here, the effect of breast cancer prediction using Naïve Bayes classifier. Naïve Bayes was found to be moderately effective classifier in the present case. Perhaps there were dependencies between the predictors. So the assumption of the Naïve Bayes perhaps was not satisfied, and that's why it has had less accuracy with the present data. Anyway, a detailed account of this and other classifiers can be found in the following book by myself and Praveen, the Advanced Statistical Manual for Ayurveda Research. This book was written in the Ayurveda context, but it is equally applicable to several other medical domains, allopathy, homeopathy, whatever. A Kindle version of this publication can be found at the following site. The details are given in the description box below. So thank you very much for listening. So please leave your comments in the comment box, and we will see next time with another classifier. Thank you.